To continue with our cats and dogs example, where we ended last time was that we separated all of our cats matrix and the dogs matrix and took the mean cat and the mean dog, and here's what they look like as pictures, okay? So what we're gonna do next is then put the two data sets back together, so we're back to looking at just the big matrix X, and we are going to PCA it, okay? So to remind ourselves, the PCA, the principal components analysis of this data matrix X, is defined as the eigendecomposition of X transpose X. Okay, so X transpose X in this case is an M by M matrix, so it's going to be 4096 by 4096. Kind of a large matrix, right? And what we get out of it is this matrix W, which is a matrix where each vector, each column vector, is a principal component of the data. And they come in order, and so the first one's more important than the second one, which is more important than the third one, and so on and so forth, okay? We also talked about last time how instead of actually computing this relatively large covariance matrix and taking the eigendecomposition of it, there's another way known as singular value decomposition where we can compute W by a different numerical technique, okay? So instead of actually computing this covariance, what we're gonna do is compute the SVD, right? And what that's gonna get us is X as represented by the product of three matrices, U, sigma, and V. And we noted that V is the same as W. So this W up here, computed as the eigenvector of X transpose X, is exactly the same as this V here. So I'm going to be using the SVD to perform the PCA, but you can think of V as W. They're exactly the same, okay? So let's go and start exploring this data set using the PCA, okay? So what we're gonna do is, once again, load up the data set. So I've loaded cats and dogs here. And something happened here. I'm not really sure what it is, but let's try this again. Oh, somehow I've slid the screen. Interesting. Let's go back to our editor. Here we go. I've loaded cats and dogs. And what we can do now is take our, so we're going to run this, and we're going to take our data matrix X and compute its singular value decomposition. So we do U, sig, and V equal to SVD of X. Okay, so I'm going to run that. Okay, it's done. That's great. Let's go ahead and check the sizes of these matrices to make sure that we know what's going on, right? So I have size of V, which is M by M, exactly like we think we should. That's good. And if we then take the diagonal of sig, remember sigma here, is a matrix where it's all zeros except for on the diagonal, and those contain the singular values. I'm going to put the singular values in the diagonal of sig, okay? And then I'm going to check the size of the singular values. So there's 242 of them. That's exactly right, because there should be, whatever the smaller of these two dimensions is, kind of determines the size of the number of singular values you have. So in this case, because 242 is smaller than 4096, we end up with 242 non-zero singular values. So that's good. Okay, so the first thing we're going to do is check out the distribution of these singular values. Okay, and like we discussed last time, this is really useful because the relative value of the singular values, the way they're distributed, is a really good way of determining where we can truncate this data set, how few dimensions we can get away with in explaining the data set, and it's also a proxy for how complex the data set is. So what we're going to do is make a figure where we're going to plot the cumulative sum of the singular values as a function of increasing number of singular values. So we're going to, first of all, normalize the singular values by dividing by its sum. So the sum of SV should now equal to 1 because I've defined it that way. And what I want to do is make a stairs plot of the cumulative sum of the singular values. And the x label is going to be singular values, and the y label is a cumulative sum. Here we go. And that's our plot. Great. Okay, so as we discussed, there's 242 singular values, which is why the x-axis goes from 0 to 250, and it ends at 242. The cumulative sum goes to 1, which is good because I've defined it that way. The last point better be 1 because I've defined it that way, and because this is a cumulative sum. Okay? And the curve actually looks relatively smooth, not because it's not a stairs plot, it really is if you zoom in closely, but because there's actually so many numbers in this plot that it's starting to look like a smooth plot, even though it is completely discrete. Okay? So a couple of things to note about this plot. One is that there's a lot of singular values that seem to matter, right? So we talked about last time how there's sort of this arbitrary threshold where you can say, oh, I'm going to take enough singular values that it accounts for 95% of my data. Well, if we applied that criterion to this data set, 95% is right there, and we'd have to take just about 200 singular values to get there, and that's the majority of them, right? So this data is very noisy, has a lot of variability. This makes sense because we looked at some of the examples, the pictures of the pets earlier, and there was a huge amount of variability, right? It was not exactly aligned. There were pets that were totally different colors, and so those correspond to values that are 1 and 0, and really they belong to the same category. And so this is a pretty messy, very variable data set. And so even though this is not exactly what we wanted in terms of, oh, we want a really nice low-dimensional representation for the information, but it's real data, right? This is what happens, and this is why we look at the spectrum, so that we have more of an intuition of what we're doing. We're going to go ahead and truncate it at a smaller value anyway, but we have to understand that, this low-dimensional representation of this particular data set does not account for anywhere near all of the variance that we would like to account for. And that's okay. That's just the way it is. And so having a recognition that that's what's happening is the important part, right? This does not mean you should not be doing PCA. You can do PCA on a block of data like that. It will work, it will compute it, and you will get an answer. So characterizing the spectrum, the singular values this way, gives us more of an intuition about what's going on. This does not say to me we shouldn't be doing PCA. Rather, it says to me this is a very complicated data set. And any conclusions we draw by truncating it, we have to be a little bit wary because it may not be accounting for all the variability in the data. Okay? So that's great, and what we're going to do now is, well, okay, so we understand that maybe the first couple of principal components may not explain all that much of the data set, but let's just look at them anyway. Let's see what they look like, right? So to some extent, what these singular values are telling us is that they're still ordered, right? The first one is still bigger than the second one, which is still bigger than the third one. And so we can still look at the first couple of principal components, and they still are the direction that accounts for more of the variance than any other direction that we can find, okay? And so the first principal component is simply the first column of our V matrix, right? Which is also the W matrix. So it's the first column of the V matrix right here. Okay, so that's PC1, right? And so what I want to draw home here is this intuition of what this really means. Okay, PC1, I've just run that code, so we can go ahead and look at the size of PC1. PC1 has the same number of elements as the number of measurements. Okay? It always does. It's in the space of measurements. It's like another picture of a pet that never existed. But to some extent, you can think of this as like a canonical pet. All right? So to drive that message home, let's look at it, right? Because it has the same dimensions as the number of pixels we have, we can literally reshape it as an image and visualize the first principal component as an image. And this is something that is kind of difficult to do if you're not working with images, which is why I like showing people this when they're first exposed to principal component analysis. So we're going to use the same color map, which is gray, and here is PC1. This is the first principal pet. Okay, these are also there's a name for these things. When people do this analysis on human faces, the principal component faces are called eigenfaces for this reason, because it's the eigenvalue of the eigenvector of the covariance matrix. I'm going to call this the eigenpet because we've done PCA on pets. So this is eigenpet 1. Notice that it's a little fuzzy. It's not super clear what it is, but it is something that resembles in shape to something that the two data sets have in common, which is that we've aligned the positions of the eyes and cropped out the head of all the pictures. And so PC1 actually picks out what is most in common of all the pet pictures that we have. Okay? So next, what we're going to do is I'm just going to look at the next couple of principal components. We'll see what they look like. So let's say we make a figure, and I want to look at the first 6 principal components. So I'm going to do a subplot where each of the subplots is going to be one of these principal components. So it's going to be the ith column of V, right? And I'm going to plot the image of that principal component. And this will plot the first 6 for me. And I'm just going to add a title for each of them so we can keep track of which one's which. Here we go. Here are the first 6 principal components. So 1 is the same one we just looked at. That was PC1. PC2 looks strikingly like a cat. PC3 is, it's kind of mixed actually. It's a little interesting, right? Because you can kind of almost see a shadow of a ghost of a cat that's in there, but it's got the forehead of a dog. And if you look at the darker regions, you can almost see the droopy ears. PC4 is looking a little messier still, right? So again, remember these are in decreasing order of variance explaining the data, right? So PC4 looks almost like a tiger. PC5, if I squint, I can see a shadow of a cat in there with kind of pointy ears. I can see the pointy ears right here. And PC6 is starting to look almost like a collie to me, but it's a little hard to tell, right? So we can go on and plot all 242 of these principal components, but these are sort of the biggest 6 of them. And it's nice to be able to visualize them as pets, as eigenpets, because they're literally in the same space as the images of every single picture. Because what we're going to do next is project each of our data points onto these dimensions. Specifically, what we're going to do next is project all of my data. I'm just going to project it onto PC1 and PC2. Not because they account for the majority of the data. They do not, as we found out. But because it's easy for visualization purposes. And we can do more analysis later on higher dimensional spaces, but it's just a little bit harder to look at, right? So what does it mean that I'm projecting my data onto PC1 and PC2? Well, one way to think about it, and I can write it down mathematically, but let's just talk about it first, right? One way to think about it is that I'm going to take every single image of my pet. I'm going to take every row of my data matrix X, and I'm going to ask the question, how similar is that image to this image? It's going to give me a number. It's going to be if it's identical, it's going to be 1. If it's completely different, it's going to be 0, right? And then I'm going to do the same thing with PC2. How similar is my image to PC2, right? And so those are going to be the numbers that I'm going to be plotting into a data cloud. I'm going to have 242 points where what each point corresponds to how similar is it to PC1 and how similar is it to PC2. And to write it down a different way, what we're going to do is take the truncated basis, V sub r, which is just the first r columns of the V matrix. I'm going to multiply x on the left-hand side and get my scores, right? So this is T sub r, and I'm going to be plotting T sub r, where r equals 2, as a scatter plot, so we can look at the distribution, right? So there's several ways of doing it, but let me just do it exactly what I wrote down because that's easy for me to keep track of. So T equals x times V, and I'm going to be taking the first 2 columns of V, right? So like we discussed earlier, T should be a matrix that has also n pets, but then instead of having m measurements, it's only going to have 2 measurements, which are the projections of how similar it is to PC1 and how similar it is to PC2. And next, what I'm going to do is plot the dots in T as as dots in this space. So that's what that looks like, right? So on the horizontal axis is PC1, on the vertical axis is PC2, and I have one dot for each pet in terms of how similar it is to each of those images that we visualized earlier. Okay? So this is good. It works. We can visualize it this way. So the next question we can ask is, well, is there any pattern in this data set? So is it the case that cats are more similar to each other than they are to dogs on average? We can ask that question, right? And so in this particular data set, because we actually have a label G of each pet and whether it is a cat or a dog in this training data set, we can ask that question by visualizing this scatter plot and then coloring each dot based on whether or not it's a cat or a dog. So let's do that. So what I'm going to do is I'm going to now make another figure where I'm going to plot, or I'm going to use a scatter plot of first column of T, so same thing as we did before. Oops, T. Second column of T. I want all of my dots to be of size 30, and I'm going to color it based on G, which is a label for cats and dogs. Remember, all the cats have 0, 0, 0, 0 in the G, 1, 1, 1, 1, 1, 1, 1, 1, 1 for the dogs. And I want all of my dots to be filled. Here we go. Oh, there we go. So let's change the color map here so that it's a little more visualizable. Here we go. It's a little bit better here. So same plot as before, PC1, PC2. I'm plotting the projection T onto each of those components, and one of the pets is blue, and the other pet is red. And you can see that they are really on top of each other. This particular data set is pretty messy, and they're pretty largely overlapping. Okay, it's at least in PC1 and PC2. Okay, so that's a little disappointing. They didn't separate like we think they might, and we're thinking now, well, where do we go wrong here? And if you think back onto the singular value spectrum, right, that thing we plotted, we looked at how much of the variance is cumulatively explained by the first K singular values. The first two singular values really did not explain all that much of the variance. Okay, so maybe the reason these are not separating and it's not really easy to tell apart the red points from the blue points is simply because, you know, we are not using enough dimensions. So our capacity to visualize this is limited, but we can at least do one more dimension. Okay, so here we go. Let's say T2, well, we can just say T, equals X times the first 3 columns of V. Make another figure, and we can make a scatter plot in 3 dimensions where we can visualize the first 3 columns of T. I want 30 G filled just like before, and the same color map. Here we go. Now this is the projection we're looking at. So why don't I go one step further and label the axes as PC1, and the second axis is PC2, and this third axis is, go away, PC3. Here we go. Okay, let's go for that. There we go. So now we can keep track of what they are. And if I take the rotating 3-dimensional space tool on this plot, I can visualize what's going on here. And what you're seeing now is something kind of interesting, right? So before, when we were looking at PC1 and PC2, which is this view, there really wasn't much separation between the red dots and the blue dots, right? But if I start turning this around, there are ways of looking at this data where I'm starting to see more of a separation, and a lot of it is in the 3rd dimension. You see that? And so what I'm talking about here is that if you look in PC3 in the Z dimension, right, it seems like the centroid of all of the red dots is a little bit lower than the centroid of some of the blue dots. So that's promising. So maybe let's ignore PC1 and PC2 and start visualizing this in PC3, 4, and 5. and see how this looks. So instead of projecting it onto the first 3 PCs, and again, the first 3 PCs are always the best 3 PCs in terms of the variance explained. But since we're trying to look for separation between cats and dogs, right, those may not necessarily be the best one in terms of explaining the differences between cats and dogs, because it doesn't know anything about the separation between cats and dogs. So let's go from 3 to 5. Okay? So there, what we're going to be visualizing is PC3, PC4, and PC5. And aha, here is the plot, right? Same plot as before, except we're just looking at different columns of T now. And I'm going to take my little rotating tool and look at these 2 dots. And as I turn it around, you can kind of almost reconstruct it in your head a little bit. And you can see that there's definitely a better separation now between the blue dots and the red dots in these 3 dimensions versus the other 3 dimensions. All right, so here again, you can see that the red dots are over here for the smaller values of PC3, the blue dots are over there. And if we were able to visualize this in higher dimensions by using more PCs, I bet that we can actually start to build up a better and better separation between these 2 clouds of dots. Okay? And so the goal here, which we'll get to with more techniques as we go on in the course, is to build on top of this architecture of reducing the dimensionality of the data set into the principal components, and then building some kind of classifier on top of this architecture of dimensionally reduced space, and seeing if we can build a set of rules for if I give you a new picture, is it a cat or is it a dog, right? And so if you look at it just in terms of points, right? So I'm going to reduce a new picture and project it onto PC3, PC4, PC5, just like I've done here. And the new picture is going to show up as a dot in that space. Right? And so one very simple but sensible way of building a classifier and being able to tell whether a new face is a cat face or a dog face is it closer to the cloud of red dots or is it closer to the cloud of blue dots? Right? There is starting to be some separation. There's a lot of contamination. It's hard to tell, right? But that would be at least a sensible first attempt at making a rule of separating cats and dogs and doing facial recognition based on eigenpets.